Hey there, in this lab we're looking at the conservation of momentum. In particular, we're going to have 5 different scenarios that we look at a couple of our dynamics carts. In those 5 scenarios, we're going to have a before and an after, or initial and final momentum of our entire system. The principle of the conservation of momentum states that in a closed system, all of the momentum should stay the same. We'll have, for instance, our carts perhaps start together, and then we'll launch the spring that's inside one of them, and they'll separate. We call this a type of explosion. Initially, they'll be at rest, just sitting next to each other. And because they're at rest, their momentum is 0. Remember that momentum is just mass multiplied by velocity. If both these objects are at rest, then their initial velocities are 0, and their initial momentum is 0. So in this example with the explosion, our initial momentum would be 0. That would be our before, or initial condition. After we shoot out the spring, then both cars are going to move away from each other with a certain velocity. We'll need to know what is the momentum of each cart and add those together to get the total momentum for our entire system after the explosion. Then what we do is compare the total momentum we had before, or initially, to the total momentum we have in our system after, or finally. We'll always have a before and an after to look at in each of these 5 scenarios that we're going to encounter. Our first scenario is the same one of the explosion that I just showed you. The next one we're going to look at is the perfectly inelastic collision. The perfectly inelastic collision is when we have 2 objects that are approaching each other somehow, and they end up colliding and sticking. So we have some Velcro on the ends of these carts, and when they stick together, they'll become one object. So initially, they may be moving towards one another. Each has its own momentum that we would need to calculate. We need to know the mass of our cart and its initial velocity. We need to know the mass of this cart and its initial velocity. They come together and stick, and then they move together as one object afterwards. And we'd have to calculate the final or afterwards momentum for our whole system. To do that, we'll just add the masses of our carts together and see what their final velocity is. Again, we're comparing the initial momentum of the whole system to the final momentum. To get the momentum for the whole system, all you got to do is add up the momentum of each object. Be careful, the direction of the velocity matters. It could be positive, that'll be to the right, or it could be negative, to the left. So if both objects are starting off moving like this towards one another, one of them is going to have a positive velocity, one of them is going to have a negative velocity. Therefore, the first one has a positive momentum, the other one has a negative momentum. You add that positive and negative value together, you get the total momentum for the system. After the perfectly inelastic collision, we're going to look at the elastic collision. To do that, the elastic collision needs to have magnets, which are actually inside the carts on this end. When the carts approach one another, the magnets are going to force them to repel, so they don't actually hit, but they still collide. Elastic collisions are really rare. They really only happen with subatomic particles, like 2 protons coming together and then repelling each other. They kind of collide, but they don't touch, so they don't lose any of their energy. If our carts hit each other, we lose a little bit of energy to maybe acoustical energy, the sound that's produced. If they hit hard enough, maybe you'd get a spark, and you'd lose some energy to light being transformed. In the case of the elastic collision, the magnets are going to prevent us from losing any of our kinetic energy. So not only should our momentum be conserved before and then after, but also the kinetic energy of our system, the kinetic energy of this cart plus the kinetic energy of this cart before should be the same as the kinetic energy they have afterwards. That's the elastic collision and the third scenario we look at. The next one is going to be a regular inelastic collision, regular inelastic, in which case we're not going to have the Velcro or the magnet to doing anything. We're just going to send the carts at each other. They'll be moving in opposite directions, so one will have a positive momentum, one will have a negative momentum, and they're actually going to smash into each other and lose some energy, and then they'll probably rebound, and we'll look at their momentum before and their momentum afterwards. Remember, each time we're just comparing what's the total momentum before, what's the total momentum afterwards. If it's conserved, then we should have the same amount of momentum before as afterwards. The last thing we're going to do is actually only going to involve one cart, and I'm going to send the cart down the track, and then I'm going to put a bunch of weight on top of it, and we'll see what happens when we've actually changed the mass of the object. So instead of having it collide with something, we'll have it moving along the track, at a certain velocity. It has a certain mass, so we can get its initial momentum. And then I'll place these weights on top of it, so now its mass changes. And we'll see how its velocity changes as well. The initial momentum we would calculate from before the weights are on top, and then the final momentum we'd calculate after we put the weights on top. So in that one, we'll need to know the mass of our cart plus the mass of our weights, and we'll need to know our initial velocity and our final velocity. For each of these scenarios, we're going to need to know the mass of our objects. So we'll put that up on the screen, the mass for each of our carts, cart 1 and cart 2. And we will also have the velocities that we're going to find for each encounter or each scenario. We're going to be using motion detectors and looking at the slope on the position time graph to get the velocity. Let's take a look at our setup. Here you can see in the middle is our camera stand, which is going to give us an overhead view. No need for us to be doing any slow motion or timing with this one because we have our measurement devices at either end of the track, which are motion detectors or sonic range detectors. I've labeled each one since we have two that's going to be connected to our tablet, our graphing tablet. This is going to be number 1, which will probably be the green colored line on the graph. That's on the left side of the track. And then on the right side of the track we have number 2, which should be a red colored line on the motion graph. Okay, we have our dynamics track here, and we have 2 carts. One of them is a spring cart. That's number 1, has the spring in it. That should be the green line on the graph. And then we've got number 2, which is just a regular cart, no spring. And remember, I have fastened Velcro on one end of each of them for the perfectly inelastic collision where they stick together. And we also have magnets in a couple of the ends to repel when we do the elastic collision. I also put these little pieces of index card here on the back of each of the carts. That's just to help the sound waves bounce off without creating too much error. We also have some other stuff we're using. These are the 2 weights that I'm going to drop on for the very last scenario. We'll put the mass of each of these up there when we get to that last scenario, when we do the weight drop. We've used some other stuff, some tape, scissors, and we've got our trusty ruler here to engage the spring for our first scenario, which is going to be the explosion, where we're starting with 0 momentum, and each of these objects or carts will now move in the opposite direction. So one should have a positive momentum after the explosion, and one should have a negative momentum after the explosion. All right, good to point out I'm using to the right as the positive direction. So put that in there. This is going to be the positive direction. So any cart moving this way is going to have a positive velocity, and it should appear as a positive slope on the motion graph. And any cart that's moving in this direction will be the negative direction, and we should see a negative slope. If they're both moving in the same direction, then they would both have a positive velocity. If they're both moving in the negative direction, they both have a negative velocity. They could at some point move in the same direction, or maybe at certain times they're moving in opposite directions. If you have a negative velocity, then you will also have a negative momentum, because the momentum is just the mass multiplied by the velocity. And momentum is a vector, it has a direction, so we need to use our pluses and minuses. Okay, we're going to start collecting data and see what we get for our explosion. Oh, right, look at that graph. So here we can see that we've got the green cart number 1. It moves to the left in the negative direction after the explosion. So we see we have a negative slope here. It's linear. This is a position time graph, so the linear slope indicates we have a constant velocity. The slope on position versus time, is the velocity. So I see my green cart that moved to the left has a negative velocity. My red cart that moved to the right had a positive velocity because it moved to the right after the explosion in the positive direction. Initially, we can see this is all before the explosion happened, before the spring shot out. So both of the position time graph functions are flat, indicating that they're sitting still. So this means beforehand, both objects had 0 velocity, their total momentum was 0, so initial momentum is 0 for the whole system. Afterwards, now we have this portion of the graph to look at, so I'm going to zoom in a little bit. Okay, remember our green cart is cart number 1 moving to the left after the explosion. We're going to analyze that first. To get its final velocity after the explosion, I just need to find the slope of this green function. So I'm going to go to Analyze, and I'm going to go to Curve Fit so that I can see what the slope, signified by the m parameter, as in mx plus b, is. It's showing me the section of the function I'm analyzing. This is linear, so I'm going to select the linear fit. And indeed it is negative. So there is the final velocity of cart 1, the green cart that moved to the left after the explosion. You can use all of these digits because we have a highly precise measuring tool here. Negative 0.49429, and this is in meters divided by seconds. You can see meters on the y-axis and seconds on the x-axis. So this is in meters per second. We need to keep the negative because our green cart has a negative velocity and therefore a negative momentum after the explosion. And when we look at our red cart number 2 that moved to the right, it's going to have a positive velocity and a positive momentum. And when we add those two momenta together, the positive and the negative one, hopefully it should add up to 0 or something very close to 0 because we started with 0 momentum initially because neither cart was moving. All right, so there is the final velocity of our green cart number 1 moving to the left after the explosion in meters per second. We're going to go back. We're going to analyze the red function now. That was the cart number 2 that moved to the right after the explosion. Give me position analysis, linear, please. And there we go. There is the final velocity of the red cart, 0.50907 meters per second. And that is after the explosion. All right, so we will do this for each of our scenarios here. This was the first one, the explosion. We know the initial momentum is 0 because the initial velocity of each cart is 0. And so we've just looked at the final velocity of each one just now. Let's move on to our next one, which is the perfectly inelastic collision. In this one, we are going to start the carts off at different ends of the track, and they will approach one another, and we will need our Velcro to be facing each other. And for this one, I'm actually going to keep cart number 2 stationary in the middle. And then I'm going to start cart number 1 over here on the left side. And cart number 1 is going to travel in the positive direction with a certain amount of momentum. And cart number 2 is going to start with 0 momentum. So the total momentum of our system to start will just be the momentum of cart 1. And then it's going to contact cart 2 and stick together. This is perfectly inelastic. And then we'll see the momentum of both carts afterwards. And we're going to compare the momentum of both carts afterwards when they're stuck together. We'll need the final velocity and add both their masses together. We'll compare that momentum to the initial momentum, which will just be the momentum of our cart number 1 by itself. All right, let's take a look at our graphs. All right, from our graph we can see our scenario ended and our data collection kept going for a while. So over around here is when the carts got to right by the red sensor and it got freaked out because they're so close to the sensor. So we're just going to zoom in and look at the beginning part of our graph right here when stuff actually happened. So let's zoom in and take a look. Aha. Okay, so initially we can see our position time graphs are flat, meaning nothing's moving. And then right in here, look at the green one. This is the green cart number 1 that's moving by itself. Notice red's still flat, so we haven't hit the red cart yet. It's not moving. So all of our initial momentum is comprised of the mass of our green cart and the green cart's initial velocity, which we can find from looking at the slope up here. So let's go find the initial velocity of our green cart number 1. There it is. It's moving to the right, so that's the positive direction. And we can get that value in meters per second for the initial velocity of the green cart by looking at our slope, indicated by the m parameter in our linear fit. Let's go back and now look at after the collision. I'm going to zoom into this portion to see if we can zoom in once more. Notice how the slope of our green cart's position versus time function changed. It got less steep. It slowed down. Remember, the steepness of the slope indicates the magnitude or amount of the velocity, how fast. So our green cart slowed down after it made contact with our red cart. The red cart was stationary up until right about here. And that's the same point at which the slope of our green cart decreased, meaning it slowed down. We're going to select a portion of our graph that indicates the position versus time graph after the collision. So this is when both the carts are stuck together. So you need to get the total momentum here by adding their masses together, the mass of cart 1 plus the mass of cart 2. And we're going to multiply by this final velocity. They should both have the same velocity since they're stuck together, so it doesn't matter which function I analyze. Both of these functions highlighted in the graph right now, red and green, have the same slope. Analyze, curve. Let's take off our green one. We've just deselected it. And let's just look at the red one. Doesn't matter which one we pick because they have the same velocity. Did I just do statistics? I don't care about statistics. Come on, Stacy, what are you doing? Curve fit. Want the slope, man. Red. Here we go. And we can, I'm actually just going to double check the green one too to make sure that they should be the same slope. So there's positive velocity right there. This should be the velocity for both of the carts because they're stuck together in a perfectly inelastic collision. So there's our velocity indicated by the slope parameter. 0.25343. Let's go and see what the green one is. Should be about the same. It may not be exactly the same. There's always a little bit of error. 0.25 something. 0.28577. So it's slightly off by 3/100ths of a meter per second. I suppose you could you can pick whichever one you want to use or average the two. We should be getting, they're connected, so they should have the same speed. We have slight error from our two separate motion detectors. Pick one of those to use or average those two values because they should have the same velocity. All right, remember again, we're looking at comparing the initial momentum of the whole system to the final momentum of the whole system. All right, let's look at our third one, which is the elastic collision. This is the collision in which all of the kinetic energy should be conserved as well as all of the momentum. Momentum's always conserved, energy not always. But because we're going to be using our magnets here, the magnets should prevent the carts from hitting each other, thereby allowing them to hopefully conserve all of their kinetic energy. I got to make sure that I have my magnets facing one another, and I need to make sure that I don't push them towards one another too quickly. Otherwise, I'll overpower the magnets and they'll actually hit. Let's flip our numbers around here. I don't know if I did that last time. We're going to start them at opposite ends of the track, and I'm going to try to push one of them faster than the other one. So each of the cars, we're going to have to find the initial velocity for each of our two different carts, both before and afterwards. So let's just kind of do a pretend run through here and make sure our magnets are working. All right, see that? We shouldn't have heard, we didn't hear anything because they didn't hit. And at focus, camera. Let's do another one real quick. All right, so these aren't touching each other. They're just getting really close, and the magnets are doing their job to help us preserve our total kinetic energy. So I'm going to start them back over here. I'm going to do my best to send, try to send the green cart number 1 faster. Could you focus, please? How difficult is that? One job, camera. try to make the cart number 1 go faster. And again, this is the elastic collision. Try to get our green one to go faster. So there's that, and okay, let's see what this looks like. Neat. Okay, so here we have, this is going to be our, look down here at the bottom graph, there's the red cart moving in the negative direction. You can see right up here the green is still flat, so I started to move the cart number 2 in red first to the left or in the negative direction, and there's a negative slope. And then when we see that red function turns into a positive slope, that means now it's moving in the positive direction. So our collision is right around here. See how we had a green positive slope? Green cart was moving in the positive direction here, and then it gets really close to the red cart, and the magnets force them to reverse direction in an elastic collision. And then afterwards, my green cart has a negative slope because it's moving in the negative direction. So to get our total initial momentum, we're going to need to take the mass of our green cart and multiply it by the initial velocity of our green cart, which we're going to get from this positive slope. Then we need to get the momentum from our red cart that's moving initially in the negative direction. That's why it's got a negative slope down here. So to get that initial momentum of our red cart, we're going to take the mass of the red cart number 2 and multiply it by this negative velocity. We've got to keep it negative if it's negative. Momentum has a direction. Add those two momenta together, the initial momentum of the green one, the initial momentum of the red one, add that together and we get the total initial momentum. And we put that number to the side, and then we're going to go look at the final stuff. So here we'll use the final velocity of the green one, which is negative up there, because now it's reverse direction, and that'll give us a negative momentum for the green cart. And then down here we'll look at the final velocity of the red cart by looking at its slope here, which is positive, because now it's changed direction and moves in the positive direction. And we get the momentum for, final momentum for green, final momentum for red. Add those together, we get total momentum final, the total momentum of the system after the collision. And we compare that final total momentum to the initial total momentum, and they should be the same. You also need to look at this one, the elastic collision. You also have to look at the kinetic energy for each one before and after, 1/2 mv squared for each of these carts, and see if it conserves its kinetic energy, because it should if it's elastic. All right, so we need to get, here's the initial velocity of our green one. That's what I'm going to do first. Initial velocity for green cart number 1, analyze, curve fit, green, linear, let's go. There's our slope value. Initial positive velocity for green cart is given right there. All right, let's look at the initial velocity for our red cart. That's going to be our negative velocity, which will give us a negative momentum for initially cart 2, that is red. Let's go. Value, linear. Let's take a look. All right, there's the initial velocity value given as the slope for our red cart, number 2, moving in the negative direction. Keep the negative. Those are our two initial velocities. Let's go take a look now at the final velocities. I'm going to highlight first the green portion, the final velocity for the green cart, number 1, which is now moving to the left after the collision. I need to deselect it. I'm also going to deselect my red one. And now we have the final velocity of the green cart number 1 coming up. Nice linear. And there is the final velocity of our green cart given as the slope. Now in the negative direction, keep the negative. And let's go look at the final velocity of our red cart. Now you see this noise down here, this little, I don't want to include that. I want to get a nice portion of my graph. Easy thing to do is to just zoom in to make sure you're getting a nice clean portion. So like, see this junk over here? We don't want that. And we don't really want this weird dip. We want nice linear right there. Let's use that. Curve fit for our red guy. We're going to get a positive velocity because now red's turned around, moved in the positive direction. And linear, here we go. There is our slope value giving our final velocity for red cart number 2 after this elastic collision. All right, we have 2 left to do. Next one is the regular inelastic. So inelastic is where you're always going to lose some energy. So this one we're about to do is just like our previous one, except without the magnets. So the carts are actually going to hit each other, which means they should lose some energy to the environment. For instance, if they make some sound when they contact each other, then some of their kinetic energy is going to be transformed into acoustical or sound energy. Momentum should still be conserved, but our kinetic energy should not be the same. So let's see which way can I do this. I don't want the magnets, but I also don't want the... Okay, we're on the tracks. All right, so we have no... we got Velcro on this side, but not on this side, so they're not going to stick. And we got magnets on this side, but no magnets on this one, so they're not going to repel. They're actually going to hit each other now. Boom. And they should lose some energy. I'm going to again try to make one of them move faster than the other, just to kind of make it clear which one is which. And yeah, let's go ahead and get our thing back up here. Okay. All right. And I'll put them at either end of the tracks. And this time I guess I'll try to make cart number 2 move faster. Doesn't really matter. Lots of different ways we could look at it. Now, cart 2 wasn't moving very fast after that, but enough that we can notice it on the graph. All right. So first thing, let's look at, this is the regular inelastic collision. So we've got momentum for each of our carts before. I can see I've got a velocity in the positive direction for my green one before the collision, and then I've got a velocity in the negative direction for my green one after the collision. That's why we got negative slope. Similarly, but reversed for our red one, has a negative slope, so negative velocity initially, and then a positive velocity moving back to the right after the collision. You see where our collision happened? This one looks nice and clean. That's right where the peak of this kind of triangle or valley, where the slope's reversed, that's when the carts change direction. Let's go find the initial velocity of our green cart number 1, which is initially moving to the right. Curve green position. We've got linear, here we go. And there's our slope value indicating the initial velocity of the green cart number 1 in meters per second moving to the right. Okay, let's get the initial velocity of our red cart. All right, there looks pretty good. Curve on red. And let's make it linear. There we go. There's the initial velocity of our red cart given by the slope. Notice it is negative because the red cart is moving to the left, which is the negative direction. This is before our regular inelastic collision for our red cart. Now we just need to get our final velocities. So I'm going to turn off each of these analyses. Go. Let's look at the final velocity of our green cart afterwards. And let's actually zoom in here just to see it a little better. There we go. We can see this is the point in time where we made contact and our slopes changed. I can tell the green one was moving faster just because it's steeper here. And now it's moving in the negative direction. So we're analyzing, here's now the final velocity of the green cart number 1, which is now moving in the negative direction. So we'll have a negative velocity and negative final momentum for the green cart number 1. Linear minus 0.34243, okay. And then we have our final velocity for our red one to look at. Looks like pretty much anywhere is okay to look at. We're going to look at this part of the graph for the red one. We try to look for the cleanest part of the graph, so we know it should be linear. So here's the final velocity for our red cart number 2 in our regular inelastic collision. Scenario number 4. Yeah, much slower, huh? All right, there's a slope indicating the final velocity, positive now, for our red cart number 2, which means it should have a positive final momentum. All right, we have one scenario left to do here, which is going to be kind of weird. I've not done this before. But I'm just going to pick one cart to use. We only need to be looking at one motion detector. I'm going to use cart number 1. And we're going to send it off in the positive direction. We're going to push it down the track in the positive direction, so it'll have some initial velocity. We know its mass, so we can know what its initial momentum is. And then I'm going to very carefully try to place both of these weights on top of it while it's moving without breaking anything. And what we've done is essentially increased the mass of our cart all of a sudden, and mass is part of the momentum calculation, mass times velocity. So if I increase the mass drastically, then in order for momentum to be conserved, if the mass goes up, then the velocity must go down in order for it to maintain the same amount of momentum. So that's what we'll be looking at. Hopefully we can see it on the graph. This might take a few trials in order for us to notice it on the graph. And these are the two. I got 2 of these weights. I just should show you pictures. I'll put them up now of the triple beam balance. I think I have to measure each one independently because they're so massive. They should be about the same. But this you'll know from those pictures, these are the mass of each one of these. You got to add that together, and then you also will have the mass of the cart that will need to be added for the calculation of the final momentum. Now let's see if I can do this. Okay, so you got a bunch of noise there at the end. Clearly we're at rest right here. Remember, this is 2 motion detectors following the same cart, so we only need to look at one of them. I'm going to zoom in, though, to right about here, because this craziness that happens over here in the red, that happens because the cart is now right next to the sensor, and it's freaking out. It's like, what's going on? So we don't want to analyze that. All right, so I'm going to go ahead and guess that this weird bump here, which isn't exactly lined up with both sensors, but this is probably the point at which I put on the weights. So we know if we're at rest here, then this is in motion, constant speed, constant speed. I'm just going to look at the green one right now. Because remember, they're both measuring the same cart. So I'm going to consider this our initial velocity from which we can calculate our initial momentum. We would just take our initial velocity from the slope here, multiply it by just the mass of the cart, because this is before we put the weights on. Let's see what we get for that. Linear, okay. Remember, we just got one cart here, so it's just, here's a positive velocity of the cart to the right before I put the weights on it. So it's just the mass of the cart and this initial velocity to get its initial momentum, 0.41743. And then see afterwards, so I'm guessing this is where I put those weights on top of it, and then you can see the slope from earlier is this black line. That's the slope we just calculated. And see how afterwards the slope is less steep. This means it has a lower velocity. So let's go highlight that, because that makes sense. We said if we add more weights to it, we increase the mass. In order for the momentum to remain the same or be conserved, then the velocity must decrease proportionately. So let's analyze now this part of the green function. Let's take that off, and then we'll turn it back on. I just did statistics, didn't I? Why would I do that? We don't want statistics. Curve fit, man. Okay, so see now we're selecting the portion of the graph after me dropping the weights on there. All right, so there's a final velocity right there for our green cart plus the 2 weights. So you got to say, if I want to get the final momentum here, you got to take the mass of the cart plus the mass of the first weight plus the mass of the second weight, and that'll be your total mass, and multiply by our final velocity, we get our final momentum. Okay. Well, there's all the data for our analysis of conservation of momentum lab. Remember, the main thing we're looking at here is what is the total initial momentum of our entire system. So if both your carts are moving, they both have initial momentum. You got to calculate the momentum of each one, add them together. That's your total initial momentum of the system. Remember, our system is just a collection of all the objects that we care about. In this case, we only have a couple objects to add together. So we want to compare the initial momentum to the final momentum, before the collision or explosion to after the collision or the explosion. The law of conservation of linear momentum states that the momentum of the system should remain unchanged if nothing else crazy comes in and acts on the system. The only forces acting on our carts when they collided was the force of cart 1 acting on cart 2 and the force of cart 2 acting back on cart 1. So there's no net external force that's messing with our carts. Therefore, it's a closed system, and the total momentum should stay the same. Therefore, the total momentum of the system should remain unchanged, or be the same before as it is afterwards. Make sure you take care to use the minus signs indicating a positive or negative velocity, because that then lets you calculate the proper positive or negative momentum. That's just given by the direction of motion of each object. So if something is moving in the negative direction, it has a negative momentum. If it's moving in the positive direction, it's going to have a positive momentum. When you add those together, it's like subtracting them. So if something has positive 5 momentum and something else has minus 4 momentum, your total momentum would be a positive 1 momentum. And those units for momentum, since it's mass times velocity, are going to be kilograms mass multiplied by meters per second, the velocity. So units for momentum are kilogram meters per second. That's it.